Okay, we're continuing looking at the various types of loads we're going to study. So the third type of load that we're going to study is point loads. Okay, so mathematically these are a bit more complicated, and we'll explain why. So again, we won't worry about the supports. We'll assume that the left of the beam is where it's supported. We'll draw the distance along the beam axis. There's not really much point drawing the other axis for this one though. Okay, well I suppose we'll just put it there so that we won't say what's on the y-axis, but we know where the x equals 0 is. So a point load at x equal to a of magnitude total load per unit length W0. Now this one is tricky. Mathematically it's quite tricky. So if I was to kind of try and explain it, I'll give it a go, but what happens is that the W0 gets lost. So you just kind of have to trust me up to a point. So let's talk about the load per unit length here. Now what we're going to do is we're going to imagine that the width of the load is a tiny number, epsilon, that's really, really close to 0. Okay, now let's describe the load per unit length here. Here it's essentially 0 in this region. Here it's essentially 0. But what about at the point here? So the load per unit length at A is equal to, the load is W0 and the length is epsilon. This epsilon is a very, very small number. Now suppose it was 18. So the width of where the point load actually touches is meant to be tiny. And no matter how small you think it is, you make it smaller. So it's like an idealized point. So say if it was a centimeter. I think we did this in a previous lecture. You had 1800. Oh, but it's meant to be smaller. Oh, millimeter. 18,000. Micrometer. What number is that? Something like 180 million. Let me just check to be sure. 18 million. What about a nanometer? 18 billion. Next one I think is called a picometer. And it just gets bigger and bigger and bigger and bigger. So this thing is essentially kind of infinite. Now to make it all precise is a bit complicated. So really I should put infinite in quotation marks, but it can be done, and essentially need something that's 0, infinite, 0, and the thing that does that is a delta function. So that's what this delta function is for. So for a point load of magnitude or even weight, W0, it'll be W0 times delta x minus a. So you need it to be really, really big at a, at x equal a, and the delta function is really, really big, it's 0. So if you sub in x equal to a into this, so let me just write down W of a is equal to W0 times delta, and you'll get, let me just sub in the x here, I'll get, oh, I don't want it at 0, I want it at a. A minus a is 0, so you get W0 times delta as 0, and if you look back at the delta function is really, really big, it's infinite at 0, so this is like your kind of infinite. It's a bit more complicated than that, but you're just going to kind of take my word up to this point. So this is the appropriate formula. Right, let's do an example. Write down the load per unit length due to a point mass. Actually, mass is probably a bit dodgy because these are newtons are genuinely weights. So I'm going to swap that out because mass is kg, whereas look, it's not too bad. Look, I just think mass is a little bit messy. Load is probably better. At x equal to 3 on a beam of length 6 meters. Now solve this to find the bending moment. Now we can imagine this is our picture. Span of 6, it's at 3. So it'll be delta x minus 3 times the magnitude, which is 13. So I have the bending moment equation here. The second derivative of the bending moment is equal to minus the load per unit length. So minus this would be minus 13 times delta x minus 3. Now from our previous lecture, we know that the antiderivative of delta is u and the antiderivative of u is square brackets. So we're going to see that here. So if we antidifferentiate, so write the inverse for antidifferentiate, we'll go from the second derivative of the bending moment to the first derivative of the bending moment. Fix the minus 13 and the antiderivative of delta is u. Now we pick up a constant. Now you will always pretty much, I don't know, do I actually write it down explicitly? It'll be written down later. It's always, the first one here is always going to be Ra. So we'll throw it in there now, the reaction at A. The only way that would fail would be if there was a point load on the support, but you're not going to see that in this module. And we'll go again. So antidifferentiate a second time. The antiderivative of the first derivative is the original function m of x. Fix the constant minus 13, and the antiderivative of u is square bracket. Antiderivative of a constant Ra. How could you get an Ra? How would you have to differentiate? It would have to be Ra times x, because the derivative of Ra times x, we'll talk about that in a second. And then the other constant that we pick up here, don't call it C1 or C2, call it MA, and it'll always be MA, I'm fairly sure. I sound fairly sure always in this module, certainly. So let's just look, if we actually differentiated this, differentiate Rax, you'd fix the Ra times, what is the derivative of x? Well, it's 1. And what's Ra times 1? It's 1. So that means everything works out there. So when solving this, we'll always have the first constant of integration here equal to Ra, and the second equal to Ma. Although this example doesn't ask for it, we can nearly always give our answer in terms of Ra and Ma. Okay, very good. So the last one here, now for my own business. This is just for me. I've got a mistake with because this should be the fourth type. Yeah, it's linear load. So a linear load is a load that goes from, say, big to small, and it varies in what's called a uniform way. Now, uniform isn't really good. I think probably the best thing for me is just to draw the picture. Okay, so let's see. Let's draw our beam again without supports. Okay, and this time we will be able to put the load per unit length on the y-axis. So we'll do small to big here. So here, this is the span of the beam here, L, and this is x equal to 0, which we don't really have to put in. It's okay. And suppose we go from, okay, let me just draw, it's probably the best thing. So say you have load per unit length here of WA, and load per unit length here of WB, and that it varies okay, I can say it varies, let's just say it varies in a linear way, and linear here meaning a line. So this kind of a shape, or a triangular kind of load would also be there. Now I would, now we've been drawing the UDLs as these things, and I think it's okay because the UDL will remind you to use U, so it's fair enough. But with these, maybe after you draw this, I recommend drawing this. Okay, maybe you say, oh, linear load. Look, I think you should just draw the line. It's not the end of the world. That's how you draw it. Okay. So what have we got here? The load per unit length at 0 is WA, and the load per unit length at L is WB. It's not hard to show that a line has a certain equation. I think we would have done this earlier in the lectures. Y equal to mx plus c. Look at it there. Y equal to mx plus c. So for us, it'll be w of x is the output. The slope, you just have to get the slope of this line, rise over run, no problem. There's a formula here, but it's just the rise over run. Times the input would be x plus the y-intercept would be WA. The slope is the ratio of how much you go up as you go across. So this is something we would have seen previously. So y equals mx plus c, it cuts at c. And if you take any 2 points and look at the rise over the run, the slope, this has to be a right angle, is equal to the rise over the run, and both or one of them or neither can be actually negative. So you just do the same thing here. You just typically you'll go between this point. Let me show you. Take this point and this point. The run is going to be the length of the beam, and the rise here will be, say, WB minus WA, which could be negative if it goes down, you see. So that's the slope. Okay, therefore you have this formula here. Now, I wouldn't recommend that you use this particular formula. I recommend you just work out it in terms of y equals mx plus c. Okay, so let's look at this example here. Write down the load on an 8 meter beam due to a linear load that varies from 10 to 26. Okay, so we'll draw a picture. And I'll nearly always recommend that you draw a picture just to help you see what you're doing. So we have distance along the beam x, and load per unit length w. Okay, and we're going, this is an 8 meter beam. Here's 8, and this is, well, this here is 8, and this is 0. And it's going from 10 up to 26. So we'll draw the 10 here, and the 26 say here. So let's 26 kilonewtons per meter here, 10 kilonewtons per meter here, and join it up in a line way. All right, and look, sure, we may as well, we can do this if we want. I don't know, do you space these out a certain amount? Maybe I'm making a mess of these and they should be 8 of them or something. Okay, but anyway, not the nicest picture in the world, but anyway. So, yeah, so the we're going to run with kind of y equals mx plus c. The c is where it cuts, is 10. And the m is the rise over the run. Now, if it goes down, the rise is negative. This is okay. What is the rise as you go from 10 to 26? Well, it's 16. And what's the run? 8. So as you go from there to there, you go up 16, divided by 0 to 8 is a run of 8, equal to 2. If it was the other way around, the rise would be, how do you get from 26 to 10? You do minus 16 over 8. And funnily enough, what you can actually go backwards if you want. So from here to here, the rise is minus 16, but the run from 8 to 0 is minus 8. So you get minus 16 over minus 8, and minus divided by minus is plus anyway. Okay. So from this, we see the slope is 2 and the y-intercept is 10. So we have wx equal to mx plus c, 2x plus 10. So we might just write out, I recommend always writing the w of x. So the equation, the bending moment equation, is the second derivative of the bending moment is minus this. So let's minus this. Let's be careful. Now to get minus this, you must multiply by minus. And if there's 2 things there, let's just do it explicitly. So minus 1 times, because how do you get minus w of x? From w of x, you multiply it by minus 1. So minus 1 times 2x plus 10. And look, the minus multiplies both of them. Minus 1 times 2x is minus 2x. Minus 1 times 10 is minus 10. So this is our minus w of x. So what we have is the second derivative of the bending moment is minus load per unit length minus 2x minus 10. And off we go. We're going to anti-differentiate both sides. So we go from the second derivative to the first derivative with an antiderivative. So we go from the second derivative to the first derivative. And we now anti-differentiate term by term, fixing constants. So fix the minus 2. Think about the x as x to the power of 1. Antiderivative of x to the power of 1 is x squared over 2. Think about what would you differentiate to end up with minus 10. It would be minus 10x. And we pick up a constant, which at this stage is always going to be Alright. And we're asked to, what does the question say? find m of x. So we've got the first derivative, we have to antidifferentiate a second time. So m of x equal to, now fixing the constant, you've got minus 2 divided by 2, that's minus 1. Which I can just, now minus 1 is the same as just minus. And then the antiderivative of x squared is x cubed over 3. Now if you're confused, I'll put in the 1, but it doesn't make any difference. Minus, fix the 10, antiderivative of x, well remember x is x to the 1, so the antiderivative will be x squared over 2. Antiderivative of RA is RAX. And we pick up the other constant of integration, or constant of antidifferentiation, is MA. Okay, so in this module, there'll never be a point load at A, and you can show that the first constant of integration is always RA, and the second one is always MA. If you want to see where that comes from, you can read this. Okay, so basically it's just saying the first one is RA, the second one is MA. So what we're going to do next is, we may as well do it here, I think we're going to have enough time, is to do a review of quadratics parabolas because they turn up. Now there's a further remark here for you which is probably relevant for if you in the second semester, but I'm going to skip it here. Okay, so quadratics and parabolas. I think we would have done a little bit on these in a previous lecture. I'm not sure exactly, so we have another bit of revision here. So this section is necessary because if you have a linear load, that's one of these yolks. Let's see what happens when we antidifferentiate it twice. Actually, we might go back here to page 72, it's just the previous page, and tidy this up. It's a little bit messy. So let's do minus x cubed over 3. 10 over 2, minus 10 divided by 2 is minus 5x squared, plus RA times x plus MA. Now what I'm getting at, there's something that I'm fairly sure you're supposed to know from your structural engineering modules, is that if you want to find where the maximum bending moment is, you find out where the shear is equal to 0. And if you have a linear load, the shear, which is the derivative of the bending moment, is a quadratic, x squared, x and constant. So we need just to do a little bit of revision of that so we know what we're doing. Okay, so because if we have a linear load, then the shear force, which is the derivative of bending moment, will be a parabola. Right. So definition, yeah, a quadratic is a thing with an x squared and x that are constant. The a has to be non-zero. One or both of the b and c, or none, can be 0. So an example of quadratic is x squared plus 1. So the main idea is that a quadratic either has a U shape, where the a is positive, or an N shape when the a is negative. It has two roots. Now what a root is, it's a number you plug into this and you get out 0. You can find them using the minus b formula. If they're both real numbers, so in other words, when you use this formula or solve this equal to 0 in a different way, if you get two real numbers, so that's numbers along the number line, so not imaginary numbers, then the graph will cut the x-axis at 2 points. So this might be the, especially this would be an a is bigger than 0, so this would be the minus b plus root, and this one would be the minus root, minus b minus square root, over 2a. The graph is symmetric about the turning point. So you get a symmetry here. Looks the same on either side. And that actually gives a different way of finding the maximum of a quadratic. So normally what you do is you'd find where the slope is 0. And that would be the min. So this would be, let's say, f, the derivative, the slope equal to 0. Or actually an alternative is to find the two roots and find the midpoint of the roots, and that will be where the max or the min is. Okay, it gives actually another way. If the b squared minus 4ac, you got square root of a negative number, you get complex roots, and you will see the graph above the x-axis. We might have a picture of that on the next page. No, we don't really need it. Okay, but the graph of plus x squared, the plus means the a is positive. the slope goes from negative to 0 to positive, and that's like a line. So if we plotted the slope of this, it might look something goes from, see, negative because it's going down in this region. At the minimum, it's equal to 0, and then after 0, it's going up, so the slope is positive. And that's the same as this thing here, negative below the x-axis, 0, and positive. And that's because if you differentiate a quadratic, you get 2ax plus b, which is of the form mx plus b. It's a line. Okay. This quadratic has two real roots where the graph cuts the x-axis, and the minimum occurs at the minus b over 2a. If you average these two, you get minus b over 2a. At this point, the tangent is horizontal. This point can be found. Okay. We need to be able to find the roots of these. In Math 7019, the quadratics usually will not have nice roots. I say simpler, I mean like nice numbers like fractions. They're going to have square roots in them. And what that means is factorizing and stuff won't work. But I'm sure that's not a problem. There's a formula, of course. The formula can always be used, but we'll see if you do the elective module next semester, you'll see that there's other reasons to factorize to find the roots of these things. It doesn't make sense to actually always use the formula. So one question is, could there possibly be two more solutions, two more roots, or any more roots? The shape of the graph says basically no. What you can show is basically that all of these quadratics have either this smiley face or this sad face, and that means they can only really have two roots. You can show this, you can show that you can rewrite this thing as this. So they look different, but actually if you multiply them out, they're the same. And what this means is that the graph of this looks like the graph of x squared. It can be shown that because of this, the graph of f of x is similar to the graph of x squared. So what that means is they'll basically look like, they'll have the U shape. They can be, I've done this before, the U shape. They can be kind of turned upside down to make an N shape. They can be shifted back and forth, and they can be shifted up and down, but the basic shape is either U or N. Now, one that doesn't cut the x-axis would be like that. That would have no real roots. That would have no real roots. You can show that, so start with x squared. So imagine this b and all this isn't there. Starting with x squared, if you change x to x plus b over 2a, that has the effect of shifting the x squared graph over. Multiplying by a has the effect of stretching it, and it might turn it upside down, and this plus pushes it up and down. None of these things change the basic U shape, bar if a is negative, it turns it into an N shape. So they all look like this, so they all can only cut the x-axis twice. Of course, we can go further and we end up with this formula. If you want to see where this comes from, take this thing, which is the same as this, and solve this equal to 0 using algebra, and you'll get this. Okay. One thing I just want to be clear on, just be careful. Make sure you use the formula properly. Here's some wrong formulas. In terms of the assignment, your answer certainly is going to have to make sense. Like if you're going to be finding a point on a beam where the bending moment is maximum, it's certainly going to want to be a value of x that's on the beam. Like if the beam is length 6 and you say that the maximum bending moment is at x equal to -3, that makes no sense. And nothing will annoy me more than giving me answers that don't make sense. When you write down an answer, you have to reflect for half a second and say, does this make sense? Okay. So, yeah, so take your time, do it properly, spend as many lines as you need, and, you know, it's all right to the bed mass crack. The other problem is, if you get a square root of a negative number, it's not a real number. That's all that you're going to say. We will see, I think, in the last chapter, some complex numbers, but basically you can ignore them. Actually, I don't think you're going to, you're not going to see it in this module. Do not change the square root of minus 81 to minus 81. That's just wrong. Square this, minus 9 by minus 9 is plus 81. Square this, whatever it is, it should be minus 81. Don't do stuff like that. If you squared a negative number, all you can say is no real roots.